Metallography has been described as both a science and an art. Traditionally, metallography has been the study of the microscopic structure of metals and alloys using optical metallographs, electron microscopes, and other surface analysis equipment. More recently, as materials have evolved, metallography has expanded to incorporate materials ranging from electronics to sporting goods composites. By analyzing a material's microstructure, its performance and reliability can be better understood. Thus, metallography is used in materials development, incoming inspection, product and manufacturing control, and for failure analysis, or in other words, product reliability. Metallography can be used in many different applications. The following examples demonstrate how metallography is such an important tool. For metals and ceramics, grain size is perhaps the most significant metallographic measurement because it can be directly related to the mechanical properties of the material. Although grain size is actually a three-dimensional property, it is measured from a two-dimensional cross-section of the material. Common grain size measurements include grains per unit area divided by volume, average diameter, or grain size number. Determination of the grain size number can be calculated or compared to standard grain size charts. Modern image analysis algorithms are also very useful for determining grain size. Twin boundaries occur when two crystals mirror each other. For some materials, twinning occurs due to work hardening at low temperatures. To correctly determine the grain size in these types of materials, the twin boundaries need to be removed from the calculation. Holes or gaps in a material can generally be classified as either porosity or voids. Porosity can also refer to the holes resulting from the sintering of metals or ceramic powders or due to the casting shrinkage issue. Voids are generally a result of entrapped air and are common in wrapped or injection molded materials such as polymer matrix composites. Defects such as cracking can lead to catastrophic failure of a material. Metallography is often used in failure analysis to determine why a material broke. However, cross-sectional analysis is also very useful to evaluate manufacturing issues which may cause these defects. Metal alloys can exhibit different phases or different homogeneous regions depending upon composition and cooling rate. Of interest to the metallographer might be the distribution, size, and shape of these phases. For composite materials, identification and characteristics of the filler would also be of interest. By slowly solidifying a molten alloy, it is possible to form a tree-like dendritic structure. Dendrites initially grow as primary arms, and depending upon the cooling rate, composition, and agitation, secondary arms grow outward from the primary structure. Likewise, tertiary arms grow outward from the secondary arms. Metallographic analysis of this structure would consist of characterizing the dendritic spacing. The effects of corrosion can be evaluated by metallographic analysis techniques in order to determine both the root cause as well as the potential remedies. Intergranular corrosion, or intergranular attack, is a form of non-uniform corrosion. Corrosion is initiated by inhomogeneous features in the metal and is more pronounced at the grain boundaries where the corrosion-inhibiting compound becomes depleted. For example, chromium is added to nickel and austenitic stainless steels to provide corrosion resistance. If the chromium becomes depleted through the formation of chromium carbide at the grain boundaries, this process is called sensitization, intergranular corrosion can occur. Coatings are used to improve the surface property of materials. Coatings can improve temperature resistance, such as with plasma coatings. They can increase hardness, such as in anodizing. They can provide corrosion protection in galvanized coatings. They can increase wear resistance and provide better thermal expansion adherence for dielectric metal interfaces. Metalographic analysis can provide useful information regarding coating thickness, density, uniformity, and the presence of any defects. Inclusions are foreign particles that contaminate the metal surface during rolling or other metal forming processes. Common inclusions include oxides, sulfides, and silicates. Inclusions can be characterized by their shape, size, and distribution. Welding is the process of joining two separate pieces of metal. The most common welding processes produce localized melting in the area to be joined. This fused area is referred to as the bead and has a cast-like structure. The area or zone adjacent to the bead is also of interest and is known as the heat-affected zone, or HAZ. Typically, the welded area will have a different microstructure and therefore different physical and mechanical properties as compared to the original metals. Analysis can also include evaluating cracks and interdiffusion of the base metals within the welded area.